Today we're reacting to Alien Biosphere Part 10 Allopatry from biblaridon. Please subscribe to him and me, of course.
This alien planet is brought to you by Campfire Technology. If you're a fan of the Alien Biosphere series and looking to make your own alien planet, or any other kind of world building or writing project, Campfire Blaze can be a big help in keeping your work organized. Blaze comes with pages to help you chart out the maps and specific locations within your world, while the Species page lets you delineate your world's native clades of flora and fauna, as well as individual facts, statistics, and miscellaneous details for every individual species. There are also tools for fleshing out the human aspects of your world, like cultures, politics, languages, religions, and magic, along with pages for narrative elements like characters, relationships, timelines, and story arcs. Blaze's free version already includes most of these features, but you also have the option of individually purchasing new modules to let you catalog your world in even more detail. To sign up for Blaze or to learn more, check out the link in the description. Over the last few episodes, we've explored each of the major biomes of our alien planet and seen how their respective ranges of temperature, precipitation, and resource availability have shaped the evolution of their resident species. But in the enormous spans of time over which evolution occurs, conditions rarely remain stable for long. As the eastern and western tectonic plates gradually drift away from each other, the supercontinent that has existed since life first moved onto dry land will finally break apart into two separate land masses. This will have several immediate effects on the climate. What was once the arid continental interior will now form new coastlines, and the proximity to the sea and the resultant increase in precipitation will turn the plains and deserts into tracts of forest. Meanwhile, the mountain ranges along the exterior coasts will continue to rise, which will lower atmospheric carbon dioxide levels through silicate weathering, and the snow and ice that accumulates on their slopes will increase the planet's albedo, leading to a gradual decrease in average global temperatures. And if these mountains, especially those in the northern plateau, see the formation of ice caps and glaciers, then for the first time in the history of terrestrial life, the planet will have entered an ice age. Up until now, the planet has been going through a greenhouse period, in which there were no polar ice caps or continental ice sheets. But as the planet cools, a cycle of glacial periods may begin, wherein for intervals spanning roughly 100,000 years, the global temperatures will drop by several degrees, sea levels will fall by as much as 100 meters, and ice sheets will advance from the poles and intrude into the temperate zones. Due to subtle changes in the planet's orbit, these glacial periods will be punctuated by relatively warm interglacial periods, each of which may last several tens of thousands of years. These drastic shifts in climate will have numerous ramifications for many ecosystems across the planet, but the breakup of the continents has another important consequence. With the exception of particularly mobile species, the respective inhabitants of the two continents are now cut off from each other, and thus evolutionary developments that occur on one continent won't affect the other, meaning they'll now have entirely separate evolutionary trajectories. Such a situation is called allopatry and occurs whenever a population becomes separated by a physical or geographical barrier, whether it be a mountain range, a body of water, or anything else that might prevent the two halves of the population from interbreeding. Since gene flow can no longer occur, a frequent consequence of allopatry is that the separated subpopulations evolve into different species, which on a global scale will result in the clades and ecosystems on the eastern and western continents gradually diverging from each other. In light of this, for the first time in this series, we're going to need to keep track of biogeography, or the distribution and range of each of our clades, particularly whether they exist on the eastern or western continent, which will be essential for determining how ecosystems form. To begin with, the overall landscape of the eastern continent will remain much the same as it was before the continent split apart, since it will remain largely within the tropics as it drifts eastward, and even during an ice age, the equator will still experience high temperatures. While stretches of tropical forest will occur along the coast, the inland areas will stay comparatively sparse, especially within the rain shadow of the eastern mountains. During the glacial periods, the forests may diminish with a decrease in rainfall, mainly surviving as patches of fragmented gallery forest separated by stretches of open plains. Environments like these allow plains-dwelling animals to live alongside forest-dwelling ones. A perfect environment for large browsers like the proceropods, as they'll be able to continuously feed on the treetops while still having enough space to move freely between areas of vegetation. When it comes to browsing herbivores, the larger the animal becomes, the better its ability to reach for food, and the more food the animal can obtain, the larger it can afford to grow. And in especially lush areas, like the periphery of the equatorial forests, this feedback loop may result in these already massive proceropods growing even bigger. To help them reach upward, their legs and pedipalps may elongate, and their foreguts may expand to contain and process the enormous volumes of nutrient-poor foliage they feed on throughout the day. To support such a huge cephalothorax, they may develop stronger muscles and hardened tendons within their back, which will attach to enlarged projections of bone along the dorsal surface of their limb girdles, functioning much like the neural spines of many large animals on Earth. Being big also acts as a deterrent to predators, and as the largest animals on the eastern continent, these proceropods will be virtually immune to attack once fully grown. We'll call these gigantic beasts stylopods. Scurrying among the feet of these giants will be a menagerie of smaller herbivores like the leptopods. Most leptopods are adapted to live in open habitats, but in this patchwork of plains and fragmented forest, some clades may evolve to occasionally wander among the stands of trees in search of food. These clades may benefit from a more generalist diet than most other leptopods, feeding not only on brachyphytes, but also on mixed caulophyte species, necrophytes, and low tree branches. The trees will also provide a degree of shelter from large steppe-dwelling predators, though they can still rely on their speed to avoid attack when out in the open. But many leptopods and other herbivores may settle on another common form of defense. We've brought up the concept of competition many times in this series, but whenever we've mentioned it before, we've been referring to competition between different species, or interspecific competition. However, intraspecific competition, or competition between members of the same species, is an equally important factor in evolution. The fewer resources are present in a species' habitat, the more intense the intraspecific competition will be to gather those resources. In environments where intraspecific competition is especially high, a species may evolve territorial behaviors, aggressively repelling other individuals from their home range to keep as much of the local resources to themselves as possible. On the other hand, though, the presence of other individuals does come with some benefits. The more animals are around, the easier it will be for them to collectively keep an eye out for danger, and the less vulnerable each of them will be to attack, since predators will be forced to pick out and go after only one target. Because of this, many species exhibit collective behaviors whereby individuals instinctively congregate in groups, which, depending on the clade and group structure, can be described as herding, flocking, shoaling, or various other terms. Along the periphery of the coastal gallery forests of the eastern continent, food will be abundant enough to keep intraspecific competition to a minimum, and so the resident leptopods can afford to evolve collective behaviors for greater safety, forming herds comprising anywhere from several dozen to over 100 members, giving these leptopods, which we'll call camptopods, a further degree of protection from the many predators they share their habitat with. The largest predators on the eastern continent will be the onychodonts, most of which will be steppe-dwelling hypercarnivores preying on a variety of big game. However, along the edges of the coastal forests, many of the local titanopods, like the stylopods, may be too large and formidable to risk attacking, so many onychodon species may specialize for hunting smaller, faster herbivores like the camptopods and other leptopods. To catch such nimble prey, they may adapt to improve their already impressive weaponry. The onychodon's greatest asset lies in their centaurism, which lets them run faster and more efficiently than other predators and frees up their forelimbs to use for manipulation. As they play an increasingly prominent role in catching prey, these limbs may evolve into specialized raptorial appendages, developing pointed serrations along their undersides to close over the prey like a vice and minimize the chance of it struggling free. As these limbs take over the role of securing prey, the pedipalps may reduce into a pair of retractable fangs that can be jabbed into the prey's hide to kill it quickly and efficiently. These eastern onychodonts, which we'll call cryptodonts, will be adept pursuit hunters in open areas, but in this landscape, the trees will be plentiful enough to provide cover for ambush predators like the Deinognathans. The rivers and watering holes may be ideal habitats for the semi-aquatic trachognathans and dolichognathans, and the fully terrestrial ancestral forms may thrive along the forest periphery. Going after plains-dwelling herbivores may bring them into competition with the onychodonts, and thus the two clades may need to undergo a degree of niche partitioning if they're to coexist in the same habitats. The Dinognathan's signature mandibles are so large and robust that they can't be used to chew or process food, this job instead being relegated to the pedipalps, which break up the food and pass it into the throat, the exact opposite condition to that of the onychodonts. Whereas the onychodonts use their pedipalps to inflict precise puncturing bites to kill their prey quickly, the Deinognathans rely on their tremendously powerful bite force to crush their prey, which may serve as a pre-adaptation for new modes of feeding. Durophagy is a feeding behavior characterized by specializations for cracking open shells, bones, or other hard structures, for which having a high bite strength is a fundamental prerequisite. As such, while the onychodonts may only be able to feed on the softer, fleshier parts of their prey, some species of Deinognathans may adapt to feed on the bones and other carrion they leave behind. For most other carnivores, these parts of the carcass would be inedible, and thus these Deinognathans will face very little competition as they evolve into durophagous scavengers. As briefly mentioned in Part 6, scavenging doesn't yield as much food as active predation, so these bone-eating Deinognathans will likely be smaller than their macropredatory cousins, and will still actively hunt prey when carrion is scarce. Durophages often have blunt, rounded teeth, an optimal shape for breaking through hard materials like bone, along with extra chambers within their digestive tract and especially powerful stomach acid. Among these Deinognathans, these adaptations may also let them crunch through the shells of plecostricans and other diplostomes, or even to subsist on tough woody vegetation. On account of having such powerful crushing jaws, let's call these animals Maleognathans. On the far side of the continent lies the coastal rainforest we covered in the last episode, which fortunately will be largely unaffected by the onset of the Ice Age, as it will still receive plenty of rainfall thanks to the warm ocean currents along the coast. It is, however, blocked off from the rest of the continent by the mountains, meaning many of the local rainforest species will exist nowhere else in the world. But a select few clades may still be able to pass over the mountains, most notably flying animals like the Opisthophorans and Pleuropterans. And since these clades have co-evolved with and helped to disperse the chromatophytes, they'll carry these plants with them as they expand their range westward, effectively bringing their own food source into their new habitats. The earliest Pleuropterans will be small generalist frugivores, but the forms that spread over the mountains and colonize the rest of the continent may grow to larger sizes and adapt for long-distance flight. The same rules of wing design that apply to the Opisthophorans will also apply to the Pleuropterans. The bigger they get, the larger their wings will need to be in proportion to their body to keep them airborne. Many of these forms may retain a similar diet to the ancestral Pleuropterans, feeding mainly on fruit and other mixed plant matter, as well as the occasional malacoform. This radiation, which we'll call the Platypterans, will comprise the majority of Pleuropteran diversity outside the eastern rainforest. But some species may spread into habitats where the chromatophytes, their principal source of food, may not be able to grow in any abundance, forcing them to adapt to new food sources. We mentioned last time how the Pleuropterans and Opisthophorans would avoid competition with each other by specializing for different diets. However, while the Opisthophorans only have their elastic spines and simple struts extending into the wing membrane, the Pleuropterans have a fully developed skeleton, which lends them enough internal support to grow much larger than the Opisthophorans can. This means that once the Pleuropterans reach a certain size, they won't face any competition if they exploit carnivorous niches, which may result in some of the more generalist clades evolving predatory behaviors. Their wings may become more pointed to give them bursts of speed when hunting, and their teeth and pedipalps may sharpen to snatch up and butcher their kills. These forms, which we'll call Theropterans, will feed on prey too big for any of the Opisthophorans to catch, such as large diplostomes, small osteopods, or even other Pleuropterans. Many of the Pleuropterans may also manage to fly across the sea and find habitats on the western continent as well, where they'll find a very different landscape to that of the east. The dry Ice Age climate will turn the majority of the continent into deserts and arid steppe, with the newly created coastline being the only area to support any sizable forests. In the inland regions, the retreating woodlands will give way to plains of tylophytes, pagophytes, and any other brachyphytes that can manage to withstand the dry conditions, with the drought-resistant notophytes forming isolated pockets of forest around lasting sources of fresh water. Such a huge change in climate and vegetation, and the oscillation in temperature between glacial cycles, will radically restructure many ecosystems across the continent. The most vulnerable animals will be ectotherms, like the ancestral platodonts, dromaeopods, and deinognathans, as they're unable to generate their own heat to combat the effects of the cold, and so many species may die off outside the tropics. Even megafauna like the titanopods may be forced into decline, as even though they're able to maintain a more stable internal temperature than other ectotherms thanks to their gigantothermy, this still may not be enough to let them contend with the constant oppressive cold and the lack of food in the inland deserts. Only the pachypods may have any notable presence in the temperate zone, as they're better equipped to deal with the cold than other titanopods due to their thick layers of fat and stocky build, but even they may struggle to survive beyond a certain latitude. On the other hand, endotherms, like the eurychirids, leptopods, and onocodonts, will have a huge advantage in the new climate, and begin taking over the vacant niches of the ectotherms in temperate areas. The bulky, cold-adapted hadrodonts may remain the dominant superpredators in the northern regions, primarily hunting large, slow prey like the pachypods. But other varieties of onocodonts, especially those that are more gracile and lightly built, may have the advantage in warmer areas. The cryptodonts would likely thrive in these regions, but since they only exist on the eastern continent, a separate clade may evolve to exploit similar niches in the west, although they may do so in a completely different way. While the cryptodonts, along with most other onocodonts, have vertically aligned pedipalps to bite down through their prey's hide, in this western clade, the pedipalps may instead evolve to oppose each other and to close laterally, acting like a pincer to securely grab prey while simultaneously inflicting lethal wounds. This means that unlike their eastern relatives, these forms won't need to use their forelimbs for restraining prey, so these limbs may shrink to allow the animal to support larger, stronger pedipalps. Let's call these forms ensidonts. But the animals that are best suited for the Ice Age will be the thylacopods and thecopods, both of which have specialized integument to complement their endothermy, and with such efficient thermoregulation, they'll thrive as the climate cools and other clades are driven from the temperate zone. But as they proliferate and spread across the continent, they'll need to face new challenges. While the tundra where the thylacopods first evolved was too cold and desolate for any predators other than the thecopods, as they move further south, they may come into contact with much larger predators like the hadrodonts and ensidonts, which may incentivize them to invest in some defensive adaptations. Since the majority of the western continent consists of open landscape, they can't rely on the cover of vegetation like their camptopod cousins, so their speed and stamina will be their primary means of evading attack. And in the arms race against the swift onocodonts, they may adapt to become even faster. The eight-legged gait of most osteopods provides a stable base, but if an animal is going to invest in speed, any superfluous legs may get in the way and present a waste of energy. Long ago, centaurism evolved in the ancestors of the onocodonts, granting them increased speed and coordination. And now, perhaps these thylacopods may convergently undergo the same development for a similar reason. Even among tetrapods on Earth, centaurism has independently evolved many times, so it's likely to be widespread on this alien planet as well. With only 6 legs, they'll be able to run more efficiently, and their newly freed up forelimbs can now be used for manipulation and gathering food along with the pedipalps. With this development, along with their unrivaled ability to tolerate the cold, this clade of thylacopods, which will give the name alabrachids, may become some of the most successful megafauna within the temperate latitudes. Where there's a relative abundance of food, like the notophyte forests along the northeastern coast, some alabrachids may exploit the niches left vacant by the titanopods, growing considerably larger and using their forelimbs and lengthened cephalothorax to reach for foliage. Their size will not only increase their feeding envelope and discourage predators, but will also increase the amount of body heat they generate, making them even more resistant to the cold. These animals, which we'll call teleobrachids, will be the largest of all leptopods, browsing on notophytes and other trees within the northern forests. Other alabrachids may retain more generalist grazing behaviors, taking over the niches of some of the basal leptopods. Like their captopod relatives in the east, species living in areas with enough food to support a large number of animals may evolve herding behaviors as a further defense against predators. But the structure of and interactions within these herds may be influenced by the thalaccopod's unique physiology. Back in Part 5, we introduced the dichotomy between R selection, maximizing the quantity of offspring with minimal parental investment, and K selection, producing smaller numbers of offspring but investing more heavily in them to increase their chances of survival. Where a species falls on the spectrum between R and K selection is a key aspect of its life history, or the pattern of survival and reproduction throughout its life cycle, which will be influenced by a variety of factors. Typically, clades will transition from R selection to K selection as they evolve larger body sizes and as their populations reach carrying capacity. So by this point in history, most species of megafaunal osteopods will likely tend towards K selection. The thylaccopods will be more K-selected than most, since the female protects her young from the cold while they're within the ootheca by cradling them with her gonopods, which gives the young a much greater chance of surviving through their development, at the expense of encumbering the mother. Note, however, that only the female bears this burden, which ties into another aspect of life history. One of the only universally applicable differences between males and females across all clades is that, by definition, female gametes are larger and require more energy to produce than male gametes, and therefore, males usually have a higher fecundity than females. This is especially true in species with internal fertilization, since once a female is fertilized, she'll be unable to mate again while she carries the developing young, further limiting the potential number of offspring she can have during her lifetime. This results in what's known as Bateman's principle, the concept that reproduction is a greater investment for females than for males, and therefore, while males are usually incentivized to mate with as many females as possible to maximize their reproductive output, females need to make sure that every attempt at reproduction will be worth the investment. This means that females will often only choose to mate with males that display an adequate degree of fitness, and who will therefore pass on their fitness to the offspring, meaning the males will need to compete with each other for the right to mate, another form of intraspecific competition. However, in the osteopods, there's the confounding factor of sequential hermaphroditism. The earliest ancestors of the osteopods were capable of changing sex during their life cycle, which many modern clades may retain. But exactly how their hermaphroditism operates will vary based on their life history strategy. Sequential hermaphrodites can be either protandrous, capable of changing from male to female, or protogynous, changing from female to male. However, this change in sex will usually only occur if it presents a potential increase in the individual's reproductive success. For example, in a population with a biased sex ratio, switching to the less common sex would present more opportunities for reproduction, and therefore, a high degree of competition between males for access to females will favor protandry. Keeping all this in mind, among the thylaccopods, the burden of carrying the ootheca while the young develop increases the cost of reproduction for the female, which will incentivize her to be more selective when it comes to mate choice, which will increase the competition among males, and ultimately lead to protandry being the dominant form of hermaphroditism among these species. The difference in reproductive priorities between the sexes may also lead to differences in their physiology as well. Sexual selection occurs when traits evolve based on their role in competing for and acquiring mates, often arising from a preference for the trait by the opposite sex. Sexual selection frequently operates differently between the two sexes, sometimes resulting in sexual dimorphism, wherein males and females of a species exhibit different characteristics beyond their reproductive system. The thylaccopods already exhibit sexual dimorphism in the shape of their gonopods, as only the female has the distinct pouch-like gonopods to help her carry the ootheca, while the males have more typical gonopods to help them fertilize the females. But sexual selection may end up driving further dimorphism. One very common dimorphic trait is body size, which is also highly correlated with mate competition. Typically, the more intense the competition between males, the larger the males will be in comparison to the females, which may therefore also be the case in these allobrachids. If competition is particularly fierce, males may also evolve horns, antlers, or other structures with which to spar with each other over access to females, which can also double as a defense against predators. In these alabrachids, the equivalent of these structures may evolve from their recently freed up forelimbs, while the females and the juveniles may simply use these limbs for manipulation and gathering food. In the mature males, these limbs may strengthen and grow hardened club-like ends to turn them into powerful punching arms, with which the males may batter each other into submission. To withstand the blows from these limbs, they may also develop reinforced bones within their skull and further armor around their cephalothorax. Due to this distinctive armament, we'll give them the name ceratobrachids. However, even if a male ceratobrachid wins a contest for a mate, he may still sustain injuries during the battle, which may reduce his chances of winning further contests, or, in extreme cases, may even result in him dying shortly thereafter. So these fights may end up limiting the male's long-term reproductive success. Because of this, another clade of alabrachids may settle for a less violent way of competing for mates. Another common sexually dimorphic trait is the presence of frills, crests, or vibrant coloration, which males use to advertise their fitness without needing to engage in physical confrontations. One clade of alabrachids may opt for this strategy, with males evolving large, colorful crests on their arms and cephalothorax to use in courtship displays. Structures like these usually have no function outside of attracting mates, and therefore come about purely through sexual selection, providing no direct benefit or sometimes even posing an active disadvantage to the individual. In a process called Fisherian runaway, a sexually selected trait may become so exaggerated that it reduces the individual's overall fitness, such as how the enormous tails of peacocks and widow birds demand a lot of energy to grow and maintain, and hamper their ability to escape from predators. At first, this seems to contradict the fundamental premise of natural selection. We'd expect males that are hindered by overly large or costly ornamentation to be less likely to survive and reproduce, and to be outcompeted by males with more reasonable, less encumbering displays. So how is it that such exuberant and costly traits can persist? The answer lies in the fact that, if a male has survived to maturity despite having such a huge and obvious handicap, then that, in and of itself, is an indicator of his fitness. So the females may maintain a preference for the trait even if males that possess it have lower survival rates than those without it, creating a feedback loop that selects for increasingly exaggerated ornamentation. Among these alabrachids, Fisherian runaway may select for larger and larger crests, which, despite the fact that they'll get in the way while feeding and make the male more visible and vulnerable to predators, will be maintained purely because of the female's preference for them. In these animals, which we'll call corythobrachids, a male's reproductive success will primarily be determined by the size of his crests, while less successful males may become female as a way of easing the intensity of the competition, shedding their crests as they do so. Along with these clades of thylacopods, the thecopods will also come to thrive in the temperate latitudes, though they'll still live in the shadow of much larger onocodonts like the hadrodonts and enzodonts. Most species may avoid competition with these clades by remaining comparatively small and inhabiting areas with too little prey to support larger predators. Where prey is especially scarce, like the cold deserts and barren scrublands that form the majority of the continental interior, the smaller, more generalist species will have the upper hand. To help them handle a wider variety of food, their mandibles, which in other onocodonts are simply designed for cutting meat into pieces small enough to be swallowed, may acquire additional grinding surfaces to help them chew vegetation as well, while the role of shearing off chunks of flesh may be increasingly played by the pedipalps, which may therefore acquire additional cusps and cutting edges, an innovation broadly equivalent to heterodonty in Earth's vertebrates. But beyond these physical adaptations, the limited availability of resources in their habitat may also have implications for their life history. Once again, Bateman's principle posits that the difference in investment between the two sexes during reproduction will incentivize the females to be selective in mate choice and for males to mate with as many females as possible. However, the lower a species' population density, the fewer opportunities there'll be for mating. So at some point, instead of wasting time and energy searching for multiple females, a male may ultimately achieve greater reproductive success by investing more heavily in a single mate. Possibly the most extreme case of this phenomenon occurs among ceratioid anglerfish, which live at such low population densities that, when a male encounters a female, he may never get another chance at reproduction, and so he permanently attaches himself to her, providing her with a steady input of sperm to fertilize her eggs. While the thecopods are unlikely to be driven to such an extreme, the scarcity of resources in their habitat will inevitably result in low population densities, which may select for increased reproductive investment in the males and ultimately culminate in the evolution of monogamy, staying with only a single mate at a time. Monogamy is quite rare as a reproductive strategy, but may evolve when females are widely scattered or if the offspring are likely to die without investment from both parents. When a male fertilizes a female, he may remain with her while she's pregnant, assisting in hunting and helping to care for the young once they're born. He may only leave once the young are old enough to survive on their own, at which point he may begin looking for another female, a behavior called serial monogamy. Another consequence of resource scarcity will be increased intraspecific competition, so to protect their access to local food sources, these thecopods might exhibit territorial behaviors. However, in the search for a mate, the male will be forced to wander far and wide, and thus it may not be feasible for him to defend a territory of his own, instead sharing a territory with the females he mates with. But the female may not accept his presence lightly. Having a male within her territory will mean she'll have to share her resources with him, which she may only tolerate if she judges him as a decent mate, violently attacking him and chasing him off if he doesn't meet her standards. Because of this heightened interest in territorial defense, the females may be larger and more aggressive than the males, and since the process of finding and acquiring a mate is a lot more hazardous for the male, finding his own territory and becoming female may present a potential increase in reproductive success, and therefore protandry will once again be the dominant form of hermaphroditism in this clade. With this life history strategy, these thecopods, which we'll call amphidonts, will be some of the most highly case-selected animals yet to evolve, letting them maintain stable populations as the Ice Age encroaches. But while the cold-adapted thecopods and thylacopods will have an advantage in the new climate, so will the clades that once inhabited the central desert, whose ability to survive on very little food and water will let them considerably expand their range as the continent dries out. The amblypods may begin outcompeting other small herbivores in arid areas within the tropics, while the lystrachirids, being adaptable enough to eat just about anything, may be able to spread into the temperate plains and scrublands. As they arrive in these more fertile areas, some lystrachirid species may increase the proportion of plant matter in their diet, with their broad, multi-purpose teeth enlarging to help gnaw through brachyphyte bulbs and tree roots. As they rely less and less on scavenging, their pedipalps, previously adapted for reaching inside carcasses to probe for fresh meat, may lose their role in feeding and assume an entirely sensory function, essentially becoming a pair of antennae. Both their fossoriality and their nocturnality will be major assets, having originally evolved as a way of escaping the desert heat, but now serving to help them avoid the higher levels of predation they'll encounter as they colonize new ecosystems. But one of the most exceptional aspects of their biology is in their reproduction. While the offspring of most other osteopods are precocial, more or less fully developed at birth, the lystrachirids are highly altricial, undergoing a significant portion of their development after they're born, with their young being blind, boneless, and largely immobile. For these young to have any chance of survival, they'll need at least some help from the parents, which in the basal desert-dwelling species came in the form of birthing the offspring within a carcass to serve as a first meal. But in these new species, this may evolve into a more dedicated form of parental care, such as keeping the young safe within a deep burrow and providing them with food as they develop. Once again, however, Bateman's principle means that a male will see greater reproductive success from mating with multiple females, and spending time and energy caring for the young will limit his ability to look for mates. So unlike the amphidonts, whose females are widely scattered enough to justify the male assisting in parental care, the role of nurturing the young may fall solely on the female lystrachirid. However, while multiple matings will maximize the male's fitness, searching for mates will expose them to many of the steppe-dwelling predators, and so an individual's reproductive potential may be cut short by an early death. If a species has an especially high mortality rate, then rather than relying on a decently long lifespan to provide multiple opportunities for mating, an animal may benefit from investing in only a single clutch of offspring early in life while it still can. Therefore, while most osteopods are iteroparous, producing multiple clutches of offspring over the course of their lives, some of these lystrachirids may evolve to become semilparous, investing all of their energy in exactly one reproductive event and dying soon afterwards. Semal parity is most commonly seen in R-selected species and is correlated with small sizes, short lifespans, low survival rates, and large clutch sizes. Semal parity is quite rare in clades with internal fertilization, especially among tetrapods, but it does happen occasionally. Likewise, iteroparity is likely to be the norm for most osteopods, but at least some of these lystrachirids, especially smaller species with high growth rates, may be some of the few osteopods to evolve semal parity. Like many animals, the lystrachirids may time their reproduction to occur during the part of the year when food is most abundant. During this time, the males may become extremely aggressive and compete furiously to find and fertilize as many females as possible, with the less successful males taking advantage of protandry to bypass the competition. The fertilized females may then dig a burrow in which to incubate the offspring, of whom they'll be fiercely protective until they're developed enough to survive on their own. Both the males and the females will begin to die off once the breeding season ends and winter approaches. The death of the adults may also help the young survive by limiting intraspecific competition between adults and juveniles. If older individuals are able to more effectively gather resources than younger ones, which will almost certainly be the case for altricial species like the lystrachirids, the juveniles may end up being outcompeted before they can reach adulthood. Having the older generation die after the juveniles leave their mother's protection will help to relieve this competition, but some species, especially those that retain iteroparity, may further avoid competition by undergoing a form of age-dependent niche partitioning. These lystrachirids are generalist omnivores, but the ability to digest vegetation requires a large foregut, which the young won't have developed yet by the time they're born. Because of this, the younger animals may be more inclined to feed on meat and other food sources that are relatively easy to digest, growing expanded foreguts and thickened teeth as they age, gradually transitioning from carnivory to omnivory. This unusual life history will give these animals, which we'll call trypanochirids, a bizarre mixture of R-selected and K-selected traits, since they simultaneously invest in large clutch sizes and high growth rates while also exhibiting parental care. As mentioned earlier, K-selection tends to become increasingly favored as ecosystems become more heavily populated and as clades reach larger body sizes. But there are some niches where R-selection is likely to be maintained. Parasitism is a form of symbiosis in which one species benefits at the expense of another, usually characterized by the parasite living on or within a host from which it derives part or all of its nourishment. On Earth, parasitism is seen in a huge number of entirely unrelated clades, although curiously is virtually non-existent among vertebrates, possibly because their physiology and life history strategies are often the opposite of what would be optimal for a parasite. Parasites tend towards small body sizes, which let them attach to hosts more easily and less conspicuously, and are usually strongly R-selected, as the biggest obstacle to their reproductive success is usually the challenge of dispersing to new hosts, which may only be overcome by producing offspring in vast numbers. Contrary to this, most clades of vertebrates are biased towards relatively large sizes, which usually goes hand in hand with K-selection, putting them at a disadvantage in competing for parasitic niches. Likewise, the osteopod shares similar specializations to vertebrates, so they too may take up parasitism less readily than other, smaller clades. In particular, the malacoforms are some of the smallest animals on the planet, and have largely maintained the R-selection of the ancestral lophostomes, making them prime candidates to evolve parasitism. The transition to parasitism may begin with phoresis or phoracy, using another organism simply as a means of transport, usually without any negative impact on the host. This may be ubiquitous among the tiny malacoforms, as hitching a ride on a larger animal will let them travel much further than they could possibly crawl on their own. But perhaps some of these malacoforms adapt to use their host not just for dispersal, but also for feeding, subsisting on the organic debris, glandular secretions, or even dead skin that builds up on the animal's hide. If these malacoforms are especially vigorous in their feeding, they may even open wounds on the host's body, which may result in some species evolving hematophagy, or blood-drinking behaviors. Blood has a very high nutrient content, making it an enticing food source for many animals. While in facultative hematophages, blood forms only a part of the animal's diet, obligate hematophages are specialized for feeding on blood exclusively. These specializations may involve optimizing the mouthparts for blood sucking and the production of chemical agents to stop the blood from clotting while the animal drinks it, maintaining a constant flow of blood as they feed. This may be accomplished in these malacoforms with sharp, toothy tentacles to bite through the host's skin and simultaneously inject anticoagulants into the wound. Hematophagy doesn't automatically qualify as parasitism, as the interaction between a hematophage and its host is often quite brief, while parasitism typically entails a long-term association. To be considered a full-fledged parasite, the animal must be adapted to remain attached to the host for a significant portion of its life cycle, which these malacoforms may achieve by evolving powerful spine-covered tentacles to securely anchor themselves to the host, and a long proboscis to bore into the skin and reach the bloodstream. The specializations a parasite undergoes will be contingent on the exact physiology of the host, resulting in co-evolution between the two. As such, many parasites are extremely host-specific, only adapted for parasitizing a single or a small number of closely related host species. So this clade of parasitic malacoforms, which we'll call mysignathans, may contain many hundreds or even thousands of different species, each one adapted to its own unique host species. But another clade of malacoforms may evolve parasitism in an entirely different way. While ectoparasites like the mysignathans attach themselves to the outside of the host, endoparasites live inside their host's body, where they're protected from the environment and are less likely to be removed. This requires a way of entering the host, which very small, especially microbial parasites may achieve by infiltrating the respiratory tract, burrowing through the skin, or even by using another parasite or hematophage as a vector. But one of the most common methods is by allowing themselves to be eaten. Among the malacoforms, many species may lay their eggs along or under leaves, where they may end up being unwittingly swallowed by foraging herbivores. If one clade evolves to produce eggs that are durable enough to survive the digestion process, some of the larvae may hatch out while still inside the herbivore, where they'll be able to feed on the contents of the animal's gut. Offering ample nutrients and devoid of predators, the herbivore will serve as an ideal incubator, prompting some malacoforms to spend their entire lives within their host. However, one drawback to this lifestyle is the difficulty it presents when it comes to dispersal. Being unable to survive outside the host means that the only way to transmit their offspring to a new host will be to disperse their eggs in the host's excrement, in the hope that they land somewhere where they'll have a chance of being ingested by another herbivore. To maximize the chances of this happening, most endoparasites once again tend toward R selection, producing enormous quantities of eggs, of which the vast majority will die. While their reproductive systems expand, many endoparasites also show a severe reduction or simplification in other body systems, as passively feeding on the host's gut doesn't require a great deal of bodily complexity, to the point that many endoparasites, like tapeworms, thorny-headed worms, and horsehair worms, have no functioning digestive or respiratory tracts, instead simply absorbing oxygen and nutrients through their outer surface. Similarly, in these malacoforms, the eye stalks and other sensory organs, being essentially useless inside a host, may atrophy completely, along with the limbs and the majority of the internal organs, while the oviduct may grow so large that it extends into the spine-covered proboscis, with which they anchor themselves to the wall of their host's intestines. This lifestyle is likely to have first evolved very early on in the history of terrestrial life, with the parasitic clades diversifying in tandem with their hosts. Like in ectoparasites, co-evolution with a host results in most endoparasites being highly host-specific, but with one major caveat. Being utterly reliant on a single host means that if the host dies, then so does the parasite, which is an especially big problem if the host species experiences a high rate of predation. Because of this, unlike ectoparasites, which are often monoxenous, completing their entire life cycle on a single host species, many endoparasites are heteroxenous, developing inside one or more intermediate hosts before being transmitted to the final or definitive host, only then maturing into their adult form and commencing reproduction. On the barren scrublands of the western continent, one clade of these malacoforms may co-evolve with a family of xerostricans, which will serve as prey for some species of theropterans. When a theropteran kills and feeds on one of these xerostricans, it may unwittingly ingest any malacoforms infesting it, which, if they survive, may adapt to use the theropteran as their definitive host. This will have the added benefit of massively increasing the range of their dispersal, since the Tharopterans can travel much further than the slow, ponderous Plecostricans can. This heteroxony means that in order to complete their life cycle, endoparasites like these often rely on their intermediate hosts being eaten. So to maximize the chances of this happening, they may produce chemical agents that alter the morphology or behavior of the host to make it more susceptible to predation, such as how the nematode Myrmica causes the abdomen of the ants it infests to turn bright red, making them more noticeable to predators, while lancet liver flukes manipulate their ant hosts into climbing blades of grass, where they're more likely to be inadvertently swallowed by cows, which serve as the fluke's definitive host. In these malacoforms, when the larvae reach maturity, they may secrete chemicals that cause their xerostrican hosts to lose their fear of predators, and to forage for food during the time of day when the Tharopterans are most active. Only once the larvae pass into the Tharopteran's gut will they develop their expanded oviducts and begin producing eggs. This may be only one of hundreds of different life cycles that develop among this clade, with every species adapting for its own sequence of hosts within its local ecosystem. We'll call them echinostomes. While it would be impossible to account for all the changes that occur as the continents break apart, the clades we've discussed here will constitute some of the major groups that will evolve over the course of about 30 million years as life in the east and west diverges. But beyond the two continents, there are some habitats on this planet that present opportunities for far more extreme forms of allopatry to occur, and whose biogeography demands a more thorough examination. In the next episode, we'll explore how life adapts to colonize the many islands across the sea, and explore the unique and highly unusual ecosystems that arise as a result. Thanks to all the artists over on...
So bye guys, in the next episode. See ya.